Hello everyone and welcome to Fleming's Math. This video covers the Day 17 warm-up as well as the Test 1 review. The first question says to sketch the graph of a function h so that the limit as h approaches 2 from the right is equal to h of 2. In other words, as you're getting close to 2 on the x-axis from the right, the y values are approaching h of 2. Which means it's approaching the y value at 2. So maybe it looks something like this. You're approaching 2 from the right, and then when you get to 2, you arrive at the y value at 2, which means you're arriving at this closed circle. The second part says the limit as x approaches 2 does not exist. So that means the limit coming from the other side, from the left side, cannot be the same as this y value here. It has to approach a different y value. So maybe something like this. Coming from the left, you see it's approaching this y value of 2, but coming from the right, it's approaching a y value of 1. And therefore, the limit as x approaches 2 does not exist. In this next problem, we're looking at the limit as x approaches pi of the cosine of 5x over 6. Well, we can just do direct substitution, replacing x with pi. And that would be the cosine of 5 pi over 6. And on the unit circle, we know that the cosine of 5 pi over 6 is negative square root of 3 over 2. All right, the next problem, we have limit as x approaches pi over 3 of the cotangent squared of x. We can do direct substitution, replacing x with pi over 3. That's going to be cotangent squared of pi over 3. So what that means is we need to find the cotangent of pi over 3, and then we'll square it. Cotangent is the x-coordinate over the y-coordinate. And at pi over 3, the x-coordinate is a half and the y-coordinate is square root of 3 over 2. That's going to simplify to just 1 over the square root of 3 because these 2's will cancel each other out. So we have 1 over the square root of 3 all squared, and that's just going to be 1 over 3. Our next problem has the limit as x approaches 0 of 3x over 2x squared. The x on the top can cancel out with one of the x squareds, and so that would just be the limit as x approaches 0 of 3 over 2x. Now if we do direct substitution, replacing x with 0, we get 3 over 0. And we know that anytime you have 0 in the denominator, that means there's a vertical asymptote at that location. So there's a vertical asymptote at 0, which means the limit does not exist. All right, in this next question, it's asking what is happening at and around x equals 2. What is happening at and around x equals 2? Here are the conditions. The limit as x approaches 2 of g of x exists. G of 2 is defined, and the limit as x approaches 2 is equal to g of 2. What that is saying is that the limit exists, so that means that the limit from the left and the right must be approaching the same point. Also, g of 2 is defined. That means there is a y value there at 2. And then this is saying that the limit, whatever the y values are approaching from the left and right, has to be the same as the y value at 2. This is what it would look like. Limit from the left is the same as the limit from the right, and when you get to 2, you do have a y value there, and that y value is the same as the limit. So what are we saying? We're basically saying that this is continuous at x equals 2. The function g is continuous at x equals 2. All right, in the next question it says, let f be the function given by f of x equals 2x times e raised to the 2x. In this question we want to find the limit as x approaches negative infinity and also the limit as x approaches positive infinity. Let's look at as x approaches negative infinity first. you can simply just replace the x's with negative infinity. And then let's use our intuition here. So 2 times x would become 2 times negative infinity, and then e to the 2x would become e to the 2 times negative infinity. Well, first of all, when you raise e to a negative power, that's the same thing as multiplying by its reciprocal. So we're going to rewrite this as 1 over e raised to the 2 times the positive infinity. Now, 2 times negative infinity is just a negative infinity. So we have negative infinity times 1 over e raised to the 2 times infinity. Well, the denominator of this fraction is exponential, and that is growing faster than the numerator is. The numerator is growing at negative infinity, but the denominator is growing at a larger infinity. So what happens when the denominator grows faster than the numerator? That means the entire fraction is approaching 0. So the limit as x approaches negative infinity is 0. Now let's look at x as x approaches positive infinity. We can replace x, both x's, with positive infinity. This is a little more straightforward. We have 2 times infinity, that's just going to be infinity. And then e raised to the 2 times infinity, that's also infinity. And so you've got infinity times infinity is just going to be a larger infinity, and that limit does not exist. All right, let's take a look at this quick reference box. What happens when we have direct substitution? In this first box, if direct substitution gives you 2 over 6, we know that that just reduces to 1/3, so that would be our limit. If direct substitution produces a 0 over 6, we know that that is just 0. If it produces 6 over 2, that's just going to reduce to 3. And if direct substitution gives us 6 over 0, we know there's a vertical asymptote there, which means the limit does not exist. Let's go to the next row. If direct substitution gives us 6 divided by infinity, well, we know when the denominator grows big, but the numerator doesn't, then the overall fraction will approach 0. Same thing for the next one. If we have 0 on the top and the denominator grows big, the whole fraction goes towards 0. If you have the numerator, the top part, getting big, but the denominator stays as a 6, then that is going to go towards infinity, which means the limit does not exist. And if the numerator is getting big while the denominator is going towards 0, then that does not exist as well. On the last row, if direct substitution gives us the 0 over 0 case, well, you remember that we just keep going, maybe using factoring techniques, etc. Same thing with infinity over infinity. We keep going by using our intuition or other techniques. And then the same with infinity minus infinity. We have to keep going to figure out what is going on with the function. And then we have the special methods. We talked about FEPL. What does FEPL represent? FEPL stands for factorials, which grow the fastest. Then you have your exponential functions, they grow fast. Your polynomials and power functions grow slow, but your logarithms grow the slowest. And this can be used when x is approaching infinity. We also have something called WMM. What does that stand for? That is what matters most, and that can be used when x is approaching negative infinity or approaching positive infinity. All right, and here's question 1. A function f is continuous at x equals 2. If f of x is equal to this expression for x not equal to 2, and f of 2 is equal to k, then k is equal to what? All right, well, first of all, we recognize that it says f is continuous at x equals 2. That means the limit as x approaches 2 of this function must equal f of 2. So basically, we just need to find the limit of this function as x approaches 2, and that would tell us what f of 2 is equal to. All right, so we begin by simplifying the expression. We recognize we have radicals in the numerator separated by a minus, so we'll just multiply by the conjugate of this numerator. So that's going to be radical plus radical on the top and bottom. Now when you multiply the top out, you're going to end up with 2x plus 5 without the radical minus x plus 7 without the radical. And in the denominator, we have x minus 2 multiplied by what's in the parentheses here. Now let's simplify the numerator. 2x minus x is just going to be x, and then 5 minus 7 would be negative 2. So we end up with x minus 2 on the top. That will cancel with the x minus 2 that's on the bottom, and that leaves us with 1 divided by this expression. Now we can bring back the limit. So it's the limit as x approaches 2 of f of x is equal to this expression. Using direct substitution, we just replaced these x's with the number 2. So that's 1 over square root of 2 times 2 plus 5 plus the square root of 2 plus 7. That simplifies to 1 over 3 plus 3, which is 1 over 6, and that must be the value of k. That's f of 2, which is k, that's 1 over 6. And this is also the limit as x approaches 2. Problem 2, the limit as n approaches infinity of this expression. Well, this is a problem of what matters most. We have in the numerator 3n to the third minus 5n. The 3n to the third grows faster than 5n does, so we can ignore the 5n. In the denominator, n to the third grows faster than 2n plus 1. So we can just ignore the negative 2n plus 1 and just focus on n to the third. Therefore, we're just focused on the 3n to the third divided by n to the third. So this reduces to limit as x approaches infinity of just 3n to the third over n to the third. Those n to the thirds can cancel out, so the limit is just going to be 3. And that's our answer. Problem 3 says, if f of x is 2x squared plus 1, then what is the limit as x approaches 0 of f of x minus f of 0 divided by x squared? Well, let's go ahead and substitute f of x with this expression. So f of x is equal to 2x squared plus 1. So we write that here. And then what is f of 0? That's plugging in 0 for x. That's 2 times 0 plus 1. Well, that's just 1. So we have 2x squared plus 1 minus 1 on the top, all divided by x squared. Next, if we simplify that, the 1 minus 1 will cancel each other out. So now we just have 2x squared over x squared. And then the x squareds can cancel out, so it's just the limit as x approaches 0 of the constant 2, and that limit is just going to be 2. All right, in question 4, we're basically looking at this graph and determining which one of these statements A through E are true. So basically, we'll just say whether they are true or false. All right, statement A says the limit as x approaches A has to equal the limit as x approaches B. Well, that is false. Let's take a look. Limit as x approaches A looks like that's approaching 2. But the limit as x approaches B, well, from the left side's approaching 2, from the right side's approaching 1. So that limit doesn't even exist. So A is going to be false. The limit of as x approaches a does not equal the limit as x approaches b. Question B, or statement B, says limit as x approaches a is 2. And that is true. Limit as x approaches a from the left and from the right. They both approach a y value of 2. So statement B is true. Statement C says the limit as x approaches b is 2. And that is false. Limit as x approaches b from the left is 2, but the limit as x approaches b from the right is 1. So the overall limit cannot be 2. So C is false. Statement D, limit as x approaches b is 1. Well, that's false. Limit as x approaches b from the right is 1, but the limit as x approaches b from the left is 2. Therefore, statement D is false. Statement E, limit as x approaches a does not exist. That is false, because the limit as x approaches a does exist, and that limit is 2. So E is false. Number 5 says the limit as x approaches 1 of x over the natural log of x. We can do direct substitution, replacing the x's with 1's. So we have 1 over the natural log of 1. And you remember that the natural log of 1 is 0. So that is going to be 1 over 0. And we know that that is a vertical asymptote, which makes it undefined or does not exist. Okay, for number 6, we see that we have a piecewise function. The first piece, or first section, of the graph goes from 0 to 2, and that's the natural log of x function. Then the second piece, or the second graph, goes from 2 to 4, and that function is x squared times natural log x. And we see that these functions change at x equals 2. So what we need to do to find the limit as x approaches 2 is to look at the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. So let's start with the limit as x approaches 2 from the left. That's going to be the very first function, because that is the function on the left. So that's the limit as x approaches 2 from the left of the first function, and that's natural log x. Using direct substitution, we simply plug in 2 for x, and we just have the natural log of 2, which is some number. Now let's look at the limit as x approaches 2 from the right. When you're approaching from the right, you're approaching the second function. So that's going to be the limit as x approaches 2 from the right of x squared times natural log x. Again, that's the second function. Using direct substitution, we end up with 2 squared times the natural log of 2, which of course is 4 times the natural log of 2. Now we can see that the limit from the left, which is natural log 2, is not the same as the limit coming from the right. That's 4 natural log 2. Therefore, we can say that since the limit from the left as x approaches 2 does not equal the limit from the right as x approaches 2, then the overall limit does not exist. All right, number 7. It says, if f is not equal to 0, then what is the limit as x approaches a of this expression? Well, first, let's factor this. So we're looking at the limit as x approaches a of x squared minus a squared over x to the 4th minus a to the 4th. What I did was I left the numerator as it is, but just factored the denominator. Now x squared minus x to the 4th minus a to the 4th factors into x squared minus a squared times x squared plus a squared. And of course you know what the x squared minus a squareds will do on the top and bottom. They will just cancel each other out. So this is just the limit as x approaches a of 1 over x squared plus a squared. Now since x is approaching a, we can use direct substitution and replace the x with a. So now that gives us 1 over a squared plus a squared, which of course is 1 over 2a squared. And that is choice B. All right, and number 8. Let f be the function given by f of x equals the natural log of x divided by x for all x greater than 0. And we want to find the limit as x approaches 0 from the right. Well, limit as x approaches 0 from the right, if we just plug in 0 for x on the bottom, and then let's think about what's happening with natural log x as x gets closer to 0. As x gets closer to 0, the natural log of x curves downward towards negative infinity. So we just put negative infinity on the top. So we've got negative infinity on the top. So that's a very large negative number, but we're getting closer to 0 on the bottom. And that means that the overall limit is approaching negative infinity, which means that it does not exist. All right, for question 9, let f be the function defined by f of x equals this piecewise function. So the first function is square root of x plus 1, and that's between 0 and 3. And then the new function, 5 minus x, goes from 3 to 5. Question is f continuous at x equals 3? All right, so in order to answer that question, we must look at the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. When we look at the limit as x approaches 3 from the left, we're looking at the very first function. So let's analyze that. Limit as x approaches 3 from the left is the limit as x approaches 3 from the left of the first function, that's square root of x plus 1. Using direct substitution, that's the square root of 3 plus 1, which is the square root of 4, which is 2. Now let's look at the limit as x approaches 3 from the right. When you're coming from the right, you are now looking at the second function, that's 5 minus x. So the limit as x approaches 3 from the right of 5 minus x, using direct substitution, is going to be 5 minus 3, which is 2. We may be onto something here. The limit as x approaches 3 from the left was 2, and the limit as x approaches 3 from the right is 2. So that means there is an overall limit. The limit as x approaches 3 overall is 2. All right, now before we can say that it is continuous at 3, we have to determine what the y value is at 3. Because if it's continuous, the y value at 3 must be the same as the limit at 3. All right, so let's take a look at the y value. What is the y value at 3? So f of 3 is going to be the square root of 3 plus 1, and that is the square root of 4, and that is 2. All right, well, let me just make sure you understand that. Why are we saying that f of 3 is the square root of 3 plus 1? That is because when x is 3, we're still using the top equation. Because you notice it says x is less than or equal to 3 for the top equation. That's why we must use the top equation for this. So we simply plugged in 3 for x in this top equation. And that gave us square root of 3 plus 1, which comes out to be 2. Well, I believe we can say that it's continuous now, because the limit as x approaches 3 is 2, and f of 3, which is the y value, is also 2. So the limit is equal to the y value, and therefore f is continuous at x equals 3.